everyone. Welcome to this episode of Eyes on Earth. Our podcast focuses on our ever-changing planet and on the people here at Eros and across the globe who use remote sensing to monitor and study the health of Earth. I'm your host, Steve Young. We have a fascinating discussion today about satellite constellations, which basically are a group of satellites working together as a system. Satellite constellations can be used to provide television service, mobile communication, or even the ubiquitous GPS that helps us navigate our cars and track our exercise. Constellations also play a part in studying the Earth through satellite remote sensing. Our current Landsat satellites, Landsat 7 and Landsat 8, operate as a system providing the same measurements over the same piece of land every 8 days. Now, individually, by themselves, each one sees the same piece of land every 16 days. But there are also satellites in orbit that resemble trains following each other closely in the same path. 438 miles above Earth, these series of satellites line up on the same orbital track and chase each other at some 17,000 miles per hour plus. NASA's Earth Observing System, or EOS, is an afternoon constellation that's an example of that. Here to talk about these constellations is Jim Lacasse, the USGS Landsat Mission Operations Project Manager based out at the Earth Resources Observation and Science Center near Sioux Falls, South Dakota. Jim has worked with Landsat in various roles since 2003, so he knows this stuff. Welcome, Jim.
Hello, Steve.
So we have two Landsat satellites orbiting the Earth up at 438 miles above the surface of the planet. What makes that distance at 438 miles so special?
Well, there's a few aspects to really answer that question. We have to look at what the satellites are trying to do. When you look at the altitude, you have to look at the resolution of the images. There's a direct relationship between the altitude of the spacecraft and the resolving power of the instruments that you're using that determines how small of an area that can be imaged. Other characteristics of the instruments on the satellites are determine how broad a range can be imaged. The combination of those things for Landsat means that they image areas on the ground that are about 185 kilometers or 15 miles wide, with the ability to pick up features on Earth with dimensions of about 30 by 30 meters, which is about the size of a baseball infield.
So the two Landsat satellites are at 438 miles. There are other satellites in that same orbit?
Well, I'm aware of about 10. The majority of them are NASA and other international NASA partners. I also found one from the Peruvian Space Agency has one up there.
And why are they all sharing the same space with us?
They all have similar requirements in terms of Earth remote sensing. Not only looking at the land, but some of them are also looking at the atmosphere and the ocean.
Apparently they want to capture kind of the same broad scale resolution of the Earth at that altitude.
Exactly.
Right. How close are they to each other? I mean, are they right on each other's bumpers or?
Well, for the A train, the afternoon constellation that we mentioned, they're as close to 40 seconds to 400 seconds is the range.
And do they need to be that close?
Yes, they're trying to get concurrent observations of different phenomena. If you fly too far apart, things will actually change in time. So you want to have those measurements as close as possible together to remove the effects of change.
Well, I think one of the things that we're interested in is sun angle and how the sun illuminates the land below. So, I mean, the closer satellites are together, the more likely they'll capture similar images with similar sun angles, right?
That is true.
Yeah, how many are at the same altitude as Landsat, and who do they belong to? Do they all follow in one right after another, or are there gaps between those groups of satellites?
Besides Landsat 7 and Landsat 8, there's also NASA Earth Science missions operating at that level, and you referred to before the afternoon constellation, which is known by the A train. And that actually was designed as a constellation with the first satellite launched back in the late 1990s. Within that constellation, the whole purpose was that there would be synergy gained by flying the satellites in close proximity to each other. Within that, there were 6 satellites, the first one being Aqua that was launched, followed by Aura. There was a French mission called Parasol, which included LIDAR for detecting atmospheric properties. CloudSat followed that, and then a joint French mission called Calypso. There was another LiDAR mission to measure the role that clouds and atmosphere play in regulating the Earth's weather. Following that, NASA worked with the Japanese exploration agency JAXA, the launch of a satellite called GCOM Weather 1, which is a global change observation mission studying the circulation of water in the atmosphere. Parasol exited the train in 2013, and then the final satellite in the constellation was called OCO, the Orbiting Carbon Observatory, and that was to quantify sources and sinks of carbon dioxide at regional scales.
So those are all in the A train?
Yes, yep, and those all just based on the science parameters they were looking at have a equatorial crossing time each time they pass over the equator, about 1:30 in the afternoon.
And so how many are in the morning train, and the morning train have a name, or is it?
Yeah, the morning train doesn't follow one after the other. They're rather in the same altitude, but they're offset such that they actually cross the same path on Earth on different days. All these satellites, even if they're not following each other in a train, they do intersect at the poles regularly.
It sounds to me like you're saying that they aren't necessarily all capturing the same data. They all have different things they want to acquire as far as information, right?
Exactly, yes. There are different sensors with different wavelengths for different purpose. Some are capturing the reflected light off the surface of the Earth, or long wavelength temperatures, or they're sounding for particles in the atmospheric column below them. Some of them can even measure wave heights out on the open ocean.
Even though what they're getting is different, I mean, collectively, all that information, all that data that's being gathered, does that provide a picture of what's happening on the Earth's surface or happening in the atmosphere?
Exactly, and that's the chief goal of all this data collection. And over time, it's really matured to where the systems are being designed to do exactly that. In the case of the A train, those instruments, when they put them together, the data was meant to be included in the algorithms of the other instruments, and that's used to in the modeling of the Earth's processes. Those models are quite complex and have a lot of data inputs. In the case of the A train, that was a specific design. But even in the case of Landsat, data from other remote sensing satellites is used. Right now, we have data that indicates the energy received at the sensor in space. What we really want are the measurements on the Earth. But since we're looking through the atmosphere, we want to be able to remove those effects. And the USGS is developing products to do that right now. Some of those inputs we get from other satellites.
So other satellites are giving us information about what's in the atmosphere that we can use to correct and remove that when the time comes?
That's correct.
I think it's well known that there's a lot of space junk up there, and every now and then satellites have to maneuver out of the way. If Landsat has to get out of the way of some space junk, do we in any way communicate with the other systems to let them know, or is everybody on their own when it comes to worrying about what might be in their path?
Yeah, each satellite and each operator is concerned with what's in their path. We do get common information from the Air Force, who's charged with monitoring space debris and the orbit of all satellites, and then providing notification to satellite operators when a conjunction is predicted.
They would provide that information not only to us, but share it with other agencies, other countries?
Yes, the Air Force provides notifications to satellite operators.
It's up to each operator to make a determination of what they want to do about it?
They tell us when a predicted conjunction is going to happen, the probability of collision, and basically the quality of data that went into calculating those numbers. And then the operator has to make a decision based on that, and it can be a difficult decision. The satellites only have a limited amount of propellant on board. Every maneuver reduces that propellant and basically takes away from the length of the mission. You can't maneuver for every predicted collision. It is a very difficult decision sometimes.
Sure. Let me ask you as the last question, Jim. We have all these different systems orbiting at the same altitude. Do we ever sit down with each other, get together, meet somewhere and talk about, things like what the mission is we're trying to accomplish, how long we're going to be up, when we're going to move out of that orbit? I mean, are there conversations about that?
Yeah, we do regularly meet with NASA, who has both the A-Train and fly some other Earth science missions, and we meet 2 times a year. Since we're operating at the same altitude, we have to basically be good citizens. If we do something to be stuck in orbit and not being able to maneuver, we affect all the rest of the people in that orbit. Things like on-orbit anomalies that could potentially leave us at 7:05 without the ability to move, or decommissioning in terms of when we're planning on getting out of that orbit. Those are critical items that we need to share and stay abreast of as a group. This is a timely conversation in that there are, as people know, more and more satellites being launched. And the commercial industry is getting much more involved. You'll hear stories of some rather large constellations being launched. One of the big ones, I won't give any names, but to provide internet around the world. And those constellations will add not only to the capabilities that we'll have here on Earth, but they're going to add to the congestion that we as space operators have. So it's going to be more and more important that we stay aware of what's being launched and keep open communication so that Earth remote sensing can continue as it has for decades now.
We have to be good neighbors, is what you're saying.
Exactly.
We've been talking to Jim Lacasse, the USGS Landsat Mission Operations Project Manager, about orbital constellations, what they are, how they are comprised, and how they might benefit humankind. Thanks for joining us, Jim.
Yeah, certainly, Steve.
We hope you come back for the next episode of Eyes on Earth. This podcast is a product of the U.S. Geological Survey, Department of the Interior. Thanks for joining us.